piece of glass. And we're going to spend a lot more time talking about how glass or different objects impact how it travels. So basically, when light impacts this glass, and unless you're told that it's something weird, you just assume that it's in air, and it's traveling at 3.00 times 10 to the 8th meters per second, okay? Our atmosphere really doesn't slow it down a noticeable amount, okay? So you just leave the 3.00 times 10 to the 8th meters per second. So the correct terminology is an optically dense medium. So the more optically dense the medium is, the more it impacts the speed of light. So if it hits a more optically dense medium, the light slows down. So we'll get into this more later, but this is the whole point of optics, is that when that light hits this, it can do one of two things. It can either get bent down like this, okay, in a direction like this, or it could get bent up where it goes like this. Now, here's the best analogy that I can give you, and it actually has to deal with wheels and axles. So, imagine that this pencil is a set of wheel and axles, and you're on dry pavement, okay? And there's dry pavement over here. But in between, there's a median in the highway that's got 6 inches of snow in it, okay? So, here's your car coming along like this. You're on dry pavement. It's going to hit this median, right? So this top part of that wheel and axle is going to hit first, right? So since that gets hit first, what's it going to do? Is this going to speed up or slow down?
Slow down.
That's going to slow down. The other side is going to keep going. So what's going to happen is that this light, if it comes in at an angle, is going to get deflected. And again, you make the analogy that this is like heavy snow, and this is the wheels on an axle. So it comes in, this side's going to slow down, and it's going to get bent towards this normal. So now everything is in there. It's going slow. Now, when it leaves, this side is going to hit the dry pavement first. So what's it going to do? Speed up or slow down first? It's going to speed up, and then so that's going to bend it back this way. So this is how all optics work. It's because of the fact that when light hits different mediums, it speeds up or it slows down. Now, if you're just at a 90-degree angle to it, what's going to happen? Nothing. Everything's going to slow down at the same rate. And then once it gets here, everything is going to speed back up. So you only get this bending when you hit it at an angle. That's going to be all of optics, which is going to be next week. So, one of the things that, and this is kind of this overarching thing, the speed of light is wavelength times frequency. So that's one equation that you need to keep in mind. The second equation is that the energy of light is Planck's constant times frequency, okay? And it is energy that determines what you see as color. It is not wavelength, okay? It is the energy. And energy is determined by the frequency, okay? So if I look out and I see Mitchell wearing a red sweater, okay? Why that appears red, and it's an anomaly about how light works. That appears red because it's absorbing every other color in the spectrum but red. Red is getting reflected off of it. So I see red because white light is being emitted, which is a blend of all the different colors in the spectrum. That red sweatshirt appears red because it absorbs every color but red. And that's what gets reflected off. Now, if you've ever been outside in the summer, why do you not want to wear dark colored clothing in the summer? It absorbs all light. So when I see like the black hoodies over here, okay, why do those appear black? They're absorbing basically all the light. So if you're outside in the summer and you're wearing a dark colored shirt, you're going to get hot. Now, I see Deacon wearing a white hoodie, okay? You want to wear light colored clothing in the winter, or excuse me, in the summer. Because if Deacon's wearing that white, basically it's reflecting off the colors, all the colors in the spectrum. So what appears as white is the fact that that basically isn't absorbing any colors, and it's reflecting off white. So what you see as a color is the fact that it absorbs every color but that, and that's what gets reflected. Okay? So that's the second big equation. So on that first question where it says, is the frequency of this wave higher or lower, okay, as it enters the piece of glass? So if the frequency changed, what would that do to the energy?
You change the energy.
You change the energy. If you change the energy, you're going to change the color. Okay? So this is what I tried to show you yesterday. I hold this up, okay, and you're over there, you still see the same color. Why?
Because the frequency didn't change.
Frequency didn't change. So, but that leads us to the next question. If frequency doesn't change, what does change? Wavelength. Okay, that's going to be important later on in some of these questions. So if you alter the wavelength, then it changes the speed. So this is a generic one when it's the speed of light. If it's anyone else, it's still wavelength times frequency. So if the new velocity is less than the speed of light, say it's 2.0 times 10 to the 8th meters per second. So if that has the same frequency and you're decreasing the velocity, what's the only way that can happen? Is if the wavelength becomes smaller. Okay, so the only variable you manipulate in this is wavelength. And we know we only change the wavelength because if we change the frequency, we would change the color. Okay? Got it? Okay, cool. So there's that question number 2, or number 1. Now, on number 2 where it says rank the following, what are you not going to have as you rank those when you write down those? Commas. So help me. If you put a comma, I will flip out. You can put less than, you can put greater than, you could put equal to.
Is that a comma?
Google those backflips before writing an F on your paper.
Yeah.
I want to see that.
Now, let's talk about question number 4. Okay? Double slit interference pattern shows fringes on a screen. This is what I showed you all yesterday. So, on a double slit experiment, you have an opening in the screen, and you have a source of some type of wave energy. It could be light, it could be sound, it could be a wave of water, okay? But here's the point. As that goes through, each one of those has a wavefront. And what's going to happen is that you're going to get 2 types of interference. You're going to get constructive interference and destructive interference. If it's light and you have constructive interference, what are you going to see? Bright or dim? So when you have constructive interference, that's when you have the brightest light. When you have destructive interference, that's what I showed you yesterday, that's when you have dim lines. And so that's what that's showing you. If you look at, let's say, for example, over here, it's referring to 17.7, but if you look down below, you've got bright lights and relative maximums and relative minimums in terms of the light. So, and again, this is what frustrates me in terms of your equation sheets, okay? So, what you need to understand on number 5 is you got the delta y equals lambda L over D, okay? Your book goes into this weird thing where it has A and all of this. This is your nuts and bolts equation, okay? It's the same one, but your book gets really weird with it. And technically, there's an M that's in there, but unless you're specifically told something different, M is just gonna equal 1, okay? So you would have to be told, hey, what's the second bright maximum? What's the third bright maximum? Something like that. So unless you're told something like that, you just assume that that's what that's going to represent. So here's the tricky part where you have to be able to think things through. So in number 4, then it says, hey, this is what this looks like on problem number 4. Then you're going to, the entire experiment is then immersed in water. Do the fringes on the screen get closer, together, or further apart, remain the same, or disappear entirely? So this is where it harkens back to this first statement. So when you immerse it in water, what's going to happen to the wavelength? Start with that idea. What's going to happen to the wavelength? Is it going to get bigger, smaller, or stay the same?
It has to get smaller.
It has to be smaller. So if you look at this equation, I'm going to make the wavelength get smaller. Okay? Wavelength is going to get smaller. Everything else is going to stay the same. Now remember, this d is the distance, that lowercase d is the distance between the two openings, okay? That is not the width of the openings, okay? That is the distance between the central line areas of that opening. If you're talking about two radio towers, which you're going to on the test tomorrow, it's going to be the first problem that you're going to encounter. That could be the distance between two radio towers that are emitting radio waves. Do radio waves travel at the speed of light or the speed of sound? Speed of light. Okay, remember that tomorrow. Okay.
How fast do you think sound?
I'm going to tell you straight up, it's going to be the first problem on the test. It's going to involve two antennas that are emitting a radio wave. Okay, this is how they used to do navigation with boats. It's a radio wave. Use the speed of light, please. Otherwise, you get a distance beyond the distance of the moon. So, L is going to be basically how far it is to what is receiving the signals, okay? And then you've got your wavelength. So let me rewrite this because that just got all horribly normal. So here's the story. So you immerse this in water. What happens to the wavelength? It decreases. So what's going to happen to the distance between the bright lines? It becomes smaller. Okay? So that's where you have to take one bit of information and apply that to this equation. Does that make sense? Cool? Okay. When you get to question number 7, okay, again, it's a double slit. You got this equation. It says, what will happen to the fringe spacing if the wavelength of light is decreased? So number 7a is the same idea as question number 4, but they just ask you straight up, hey, what happens if you shrink the wavelength? Now, on B, it says, what's going to happen to the fringe spacing if the spacing between the slits is decreased? That's going to be changing the value of lowercase d, okay? That's going to be the changing, look where d is in the equation. When you get to C, what's going to happen to the fringe spacing if the distance to the screen is increased? So there's that value of L, okay? So, and again, on number 7, you only had to do A through C. Stop there.
So be the same.
Going Welsh.
Yeah.
Anyway, When you get to number 6, let me point out one thing on question number 6.
Oh, that's 5.
So, the width of both slits is then doubled without changing the distance between their centers. So in other words, let's say your first setup was something like this. Okay? And this was solid in between. So that energy is only going to go through those two openings. Okay? So what's going to happen on the next one is that these distances between these is going to stay the same. But then I'm going to have a wider opening that the light can come through. Is this width of this opening in the equation?
No.
No. Okay? The only thing in the equation is lowercase d, which is the center to center. But, what's going to happen to the amount of light or energy, no matter what it is, that's going to be able to pass through those openings? Yeah, you're going to have more photons going through. You're going to have more energy going through there, right? So as you have more energy, as you have more photons going through there, what's going to happen to the intensity of the light that shows up on the wall? Yeah, it's just going to get brighter. Okay, so mathematically nothing's going to change, but you're letting more photons go through. You okay?
He's getting possessed there for a little bit.
I get it.
Had to throw some cold water on me.
On the problems. So on number 3, you've got to look up the index of refraction. Actually, they gave you the index of refraction. So basically, what's going to happen on number 3 is this. Is that you've got these different layers and light's going to go through them. Obviously, your answer is going to be a really, really, really small number. Okay? So, to a certain extent, this is a distance equals velocity times time problem. So, the trick here is that you have to find the velocities in the new materials. When are you going to have your maximum velocity of 3.0 times 10 to the 8th meters per second? What's the only situation?
And a perfect vacuum.
Air in a vacuum. Okay? So you know when it goes through that glass, the oil, whatever, that with those bigger indexes of refraction, what's it going to do? Speed up or slow down? Slow down. So basically, you're going to go through and you're going to find those new velocities. So your time is going to be distance divided by velocity, which is going to be that distance. If you want to get fancy, you can write that as the index of refraction. You can incorporate that and then go from there. Anyway, your answer to number 4 is something times 10 to the 8th and a horrible GPA.
That's pretty average.
On number 4,
4A.
I mean, it should be a horrible GPA.
Yeah.
4A,
Yes, it is.
4A.
GPA is going to look after this class.
4B would be a great GPA.
If you get one of the, but I'm just telling you, if you got 4A right, you probably have 4B right.
Okay.
So your answer to 4A should be horrible GPA times 10 to the 8th.
And B should be times 10 to the 14.
Okay? Now, on number 7, okay? So let's talk about what you have this symbol, which means what?
Linear density.
I'm being facetious. I'm being facetious.
Quit using
Which
big
is
words.
10 to the negative 6, okay?
Facetious?
So on this one,
I'd be facetious.
and this is what gets weird with how they change the equations. This is why you kind of need to combine a couple of these. So you have d sine theta equals m lambda. So your book has this as like uppercase D. Every other one I've ever seen in the world has it as lowercase d. I don't know why they got weird. So on number 7, you need to find that angle. So that's just going to be, and the other key to this is that you've got, what is the angle if m equals 2? So what you're trying to find, so here's this opening, and over here is your screen, and these lines are going to intersect, and you're trying to find that angle. Now, realistically, this is how we measure this, the wavelength of light, because it isn't like we can actually like stop light in place and, oh, here's the wavelength, and we can take a little ruler and measure it. This is actually the practical way to measure the wavelength of light, is that you have it go through 2 openings, you measure the angle, then you pick whatever m value that you want, 2, 3, whatever, then you measure that angle and then you solve for wavelength. So this is the practical side of how we actually find the wavelength of light, because we can't physically measure it. So we use this equation and we go from there. Your answer to number 10, and that should be in, it should start with a 1. How about that? It depends on what you want to put that in meters or millimeters. But the first digit on number 10 should be a 1. Okay? Now, number 12 is the easiest problem on the assignment. Okay? There is no calculations to do on number 12.
Are you serious right now? Wait, you don't have to like prove?
No.
What?
Dude, you just have to solve this calculation because m is 1.
Okay, because look, so the whole key to this is that it's a double slit experiment, right? So you have one light traveling like this, you have the other light traveling like this. Obviously, one has to travel a greater distance than the other does. So if they're going to reinforce each other, and you're going to produce a relative bright line in the spectrum, okay, when you look at it, you're going to get a bright line. Clearly, they have to match wavelengths, okay? Like one has to be off a minimum of one wavelength from the other one, okay? Because that's the only way that they can match up to reinforce each other at the end and have constructive interference. So this has to be a difference of one wavelength. So what's the wavelength on number 12?
It just happens to be.
550. There's your answer.
Nanometers.
Yes. That's it.
550 squared is what?
That's why it says you need to label on your chemistry.
Is it fine if I put -7 so that we know?
That's
It's just like a good box it off.
I might change it to like that.
Gigameters.
Are we good?
Hi.
That's pretty much everything.
What?
All right.
Oh, yeah, I love that.
So Andrew, stop.
Million.